Hi guys, welcome to today's video. Today we are going to discuss about DPCM, that is differential pulse code modulation. Do you know what is a PCM? On PCM we have many steps, that is sampling, quantization and encoding. In DPCM also we can see all these steps. Along with that there will be a prediction filter too. Okay. Just have a look at what is DPCM. Why we choose DPCM? That's the first question. Why use DPCM? It's nothing because the bandwidth requirement for DPCM is comparatively very less when compared to PCM. Also the quantization error is reduced by the usage of prediction filter, as the prediction filter will predict the value of the previous sample. Okay. Then the present sample value is also calculated by using that value. The number of bits, that is bit rate, is used to represent one sample is also less. These are the advantages of DPCM over PCM. Okay. Then going to quantization error part. What is quantization error? It is the error that is caused during the quantization process. Its equation is delta square by 12. We know that delta is equal to VPP by 2 raised to n. What is n? N is number of bits, and that's equal to VPP by L. What is L? It is the number of levels. VPP is the amplitude or the maximum amplitude or the maximum voltage. Okay. As the step size, that is the delta, gets increased, the quantization error will also increase. This will lead to the distortion of the signal and the communication process will be completely in error. Am I right? So, in order to reduce error, as delta is directly proportional to VPP and inversely proportional to N as well as L, we have to either reduce the delta using either we have to reduce the VPP, or we have to increase the number of bits or number of levels. So, in order to reduce error, if we prefer the number of bits is taken more, what happens? The bandwidth will get increased. As number of bits increases, the bandwidth get increased, because bandwidth is equal to number of bits into the maximum frequency component. Okay, so as number of bits increases, the bandwidth increases. So we cannot employ this because bandwidth cannot be exceeded without or over a limit we cannot exceed the bandwidth. So that we will prefer we will prefer reducing the VPP. Why we reduce VPP? As the VPP is reduced, the delta gets reduced, so that delta square gets reduced, as well as the quantization error will reduce. This process is known as DPCM, that is differential pulse code modulation. That is, as the name suggests, the difference between the adjacent samples are taken and it is transmitted. If there are two samples, that is it may be 2 volt and 3 volt, what is the difference? It's just 1. That difference is taken and it's transmitted by encoding. Am I right? Okay. Let's just discuss about what is DPCM in detail. DPCM samples the analog signal and then quantizes the difference between the sampled value and its predicted value, then encodes the signal to form a digital value. At first, it will sample the signal as the PCM, then it quantizes. What will be quantizing? The difference between the sampled value and the predicted value is quantizing. In the PCM, we were just sampling the value, just quantizing the value that is sampled. Here we are just we are just quantizing the value that has been sampled, not the value of the sampled signal. It's the difference is getting quantized. That's the only difference. Only the difference is quantized here. In the PCM we were quantizing the sample itself. Okay, and at last the process that is taking place is the same, that is encoding will take place. If redundancy is reduced, then the overall bit rate will get reduced and number of bits required to transmit one sample will also gets reduced. What is bit rate? It's the number of bits that is required to transmit one sample. As the bit rate reduces, the number of bits get reduced. This process, this type of digital pulse code modulation technique is known as differential pulse code modulation. It is not clear by this definition alone. We have to look at the block diagram for more explanation. The principle used here is prediction. By only seeing these words, you will not be understanding anything. It's better to look at the block diagram and understand. This is a block diagram. Here we can see the sampled input is coming to the block diagram. In the PCM we have only the sampler, then quantizer and then encoder. Here we have a sampler that's not shown in this figure. Sampler, there is a comparator, quantizer, predictor, again a comparator, and then output is produced. Okay. What is coming to the comparator? The comparator is just placed before the quantizer. To the comparator, x of nts, what is this? That is a sampled input. When x of t is getting sampled, we will get what? The x of nts. This x of nts, as well as here the predictor filter will predict the value of the previous sample as x dash of nts. X dash of nts is added with x of nts and will produce error signal. Okay, the error signal is produced. It is x of nts minus, added means here it is subtracted. Here this is a summer, comparator is a summer, here it is subtracted. X of nts minus x dash of nts is producing the error signal x of nts, and this error signal is given to the quantizer input. This quantizer will be having a quantization error, that is q of nts, and this error as well as the quantization signal q of nts will produce eq of nts, that is the output of the quantizer, and this quantized error signal is being encoded to the output and is transmitted. This is the transmitter part block diagram only. On the receiver part we can see another block diagram, and this EQ of NTS is again taken back and is added up with a summer or a comparator, and this is added with x dash of NTS, and these two are added and will produce xq of NTS. That is the predictor filter input. Okay, xq of NTS will be the sum of x dash of NTS plus EQ of NTS. Okay. Then we have to look at the equations. This is x of NTS. X of NTS is nothing but present sample signal, then x dash of NTS, that is the predicted value of the previous sample, then E of NTS, error signal that we have seen, EQ of NTS, quantized error signal, then XQ of NTS, present signal that is calculated from previous predicted sample, then X dash of N plus 1 TS, that is the next value of the prediction. Okay.